Hello, I'm Patrick Holpert. I'm an associate professor in economics at the Department of Economics and Business at Kalamazoo College. As a teaching economist, cognitive load theory makes a lot of sense to me. And the reason is because we can frame it as a constrained maximization problem. What we're trying to maximize is, of course, student learning. And what we have to control is the intrinsic load, the extraneous load, and the germane load of the material that we are introducing. But we are constrained by the limited capacity of students' working memory. I think of learning as when students can use concepts and skills that I taught in my class long after they leave the classroom and in situations that are different from my classroom environment. We know that learning implies an actual change in this learner's brain. And given that the brain of our students will change, it makes sense that we as teachers understand a little bit about how the student's brain works when we try to teach them. Of course, before we even think about what content to present and how to present it, we have to remember that no student will learn effectively in our classes if we cannot create a learning environment in which students feel both safe, they have a sense of belonging, and they're also motivated to be engaged in the material that we're presenting. This is very important, of course, but it's not the focus of what I want to talk about today. So if you assume that we have achieved that, which is not easy, but now we have to decide how are we going to design our classes in order to promote maximum amount of learning. This can be very complicated because we have to ask ourselves questions such as, who are our students? What material will we teach? When will we introduce the material? How are we going to introduce the material? And also basic questions like, why are we doing it this way as opposed to some other way? Again, to me, cognitive load theory provides a useful framework in which to discuss and answer these kinds of questions. So that's what I want to talk a little bit about today. According to cognitive load theory, in order for teaching to be effective, that is, promote the maximum amount of learning, we have to carefully align the learning environment with the student's cognitive architecture. That is, the learning environment has to fit or match how the students' brains work. And the most important consideration is the very limited capacity of a student's working memory. According to cognitive load theory, in order to learn new information, the information, facts, concepts, skills have to be organized and stored in the learner's long-term memory. The problem is that in order to get into the long-term memory, the new information has to first go through and be processed by the student's working memory. And our working memory is extremely limited in both capacity and duration. We can only hold 7 ± 2 items or chunks of information in our working memory at a time. And if we don't rehearse, that information will go away in about 15 to 30 seconds. However, if we manage to process information in our working memory, then it will go into our long-term memory and it's basically stay there forever. The capacity is basically unlimited. And learning has happened. However, if the new information exceeds the working memory's capacity, the students will experience cognitive overload and their learning will be diminished or they won't learn anything at all. So the question is, what can teachers do to get the new information past the working memory and into the long-term memory so that learning will have happened, the learning will be long-term, and you'll be able to use that information in new situations, whatever you're going to be experiencing after school? And the answer is, in general, to help them construct domain-specific knowledge structures, what we usually call schemas. And that's going to happen in their brains. So then we're going to help them construct these schemas, and we want to help them make it more automatic so that they can use it more effectively. And if we can achieve that, then learning will happen, and students will be able to use the information that we have taught them more easily in the future. To implement this, cognitive load theory has distinguished between 3 types of cognitive load. We have the intrinsic cognitive load. This is the the complexity. It has something to do with the complexity of information. The number of elements or chunks of information that a student would have to process simultaneously in order to understand the material. Intrinsic load is in general unchangeable. It's intrinsic to the material. And then we have extraneous cognitive load. This is wasted cognitive load. This is when we present something in a way that adds to the cognitive load of the student, but it doesn't help them learn the material. And then finally, we have the germane cognitive load. This is the good stuff. This is how, any kind of, the cognitive load of any kind of activity that will actually help students learn. And the way we define it is to construct these schemas and make them more automatic. And that's then what we want to do. As a teaching economist, I view the problem that cognitive load theory proposes as a constraint optimization problem, where we're trying to optimize learning subject to the constraint of a very limited working memory. And the choice variables we have is the intrinsic load, the extraneous load, and the germane load. The optimal solution to this problem is actually quite straightforward. What we need to do, given the intrinsic load of the material, is to set the extraneous load equal to 0. And then we want to make sure that the germane load is equal to the cognitive capacity of working memory minus the intrinsic load. If we can do that, then that would maximize learning according to cognitive load theory. Of course, that might be impossible to achieve that optimal solution, but what can we do to move in the direction of reducing extraneous load and increasing germane load in order to promote learning? And that's what we need to be thinking about. The first decision we have to make is what we will be teaching and when will we introduce it. Any concept or chunk of information has an intrinsic cognitive load that is determined by how many elements that you have to keep in your memory, your working memory, at the same time to understand the concept. And this intrinsic load can, in general, not change. It's intrinsic to the material. However, what we as teachers can control is the impact on the learner's working memory, because that impact depends on the learner's level of expertise relative to the new material. For example, when we present a particular unit of information, somebody who has a lot of expertise, maybe a major in our discipline, will think that's just a chunk of information, whereas a novice will say, wow, that's a lot of things and I don't really know what's going on. So the intrinsic load of a particular piece of information depends on the level of expertise of the learner. So, for example, here's a diagram. As economists, we look at this diagram to the left, and we just see demand and supply framework where supply is decreasing. And as soon as that's like one piece of information, and we can just take that chunk of information and apply it to, say, the problem of Hurricane Harvey and how Hurricane Harvey will impact the price of gasoline. However, for an Econ 101 student, that diagram might just look like a whole bunch of different chunks of information that are supposed to fit together in some way, but they don't know exactly how it works. And therefore, the cognitive load of that diagram is much, much greater for a novice than it is for an expert. So, maybe a student, you present that and maybe they can actually solve the problem if you walk them through it or if you give them enough time to shift curves and figure things out. But the problem is that that action is increasing the cognitive load so much that solving the problem is too complicated and there is not enough cognitive load in the working memory to process the information and actually have learning occur. That is, they will not be able to replicate that in the future. So when we teach, we need to do a few things. First, we have to carefully choose the content to match the intrinsic cognitive load of the material to the level of expertise of the students. This requires us to reflect not only on the material, but also on who our students are. We might even have to do some pre-testing to figure out what the students know already. Obviously, this can be very difficult if we have a class that consists of both first years and seniors, or novices and majors. But our goal is to find this zone of proximal development that Vygotsky talked about in order to match the complexity of the material to the level of expertise of the students. We also need to carefully build up the knowledge structures, the schemas of our students. So what we do is present simple stuff and then we become more and more complex, or we go through the parts first and then we put them together into a whole. For example, for demand and supply, what we would do is go through the parts. We talk about demand, we talk about supply, then we put them together and we find their equilibrium, and then we can shift something and see what happens, right? So we take the parts and we put it into the whole in order to manage the cognitive load of our students. Another thing we need to do is to allow for time. We have to give the students the amount of time that is required to process information. This is actually something that gives us an argument for why we should not lecture. Because when we lecture, students will have to learn at the pace of our talking. And also it might be an argument for why we should use a flipped classroom, because a flipped classroom, they can watch the videos or read the book at their own time, and therefore they can go back and forth until they have indeed processed the information. Let me give you an example. So Lucas, my oldest son, he's learning to drive right now. So, sometimes I ask him to drive me to the store. So I tell him, turn left over here, turn right, slow down, stop here, turn right. Eventually we get to the store, we buy the stuff I needed to buy, and we go back into the car. And then I ask him, okay, Lucas, you just drove here. Let's drive back. And you know what? He has no idea how to get back home. And the reason is, of course, that the cognitive load that he required to drive, listen to me, give directions, paying attention to everything, was not enough for him to actually process that information and learn from it. So when he sitting there in the parking lot, he hasn't learned anything. All he did was just follow directions and go wherever I told him to go. And I'm arguing that our students are often the same way. Another important consideration for teachers is how to present the material. And the reason is that the presentation mode actually adds cognitive load to our students' working memory. It is possible that the way we present material adds to the cognitive load of our students so much that there is nothing left for them to process the material that we're teaching them. So what we need to do is then reduce the extraneous load of our presentations and the presentation mode in order to leave some space left over for students to process the actual material that will help them learn for the future. Here's an example. This might be a PowerPoint that we use in economics, where we have a diagram of a demand and supply to the left here, and then we have a text that describes what happens in the diagram. And our thinking might be, well, here we present the material in two different ways. That's going to make it easier for students to learn the material. It's going to be twice as good because they have both a diagram and a text that tells them what happens. But unfortunately, based on what we know about working memory, putting those two things and trying to combine them, and all the split attention effect that comes from trying to incorporate a diagram with text, is so great for a novice student that they experience cognitive overload and they don't learn anything. So when we teach, we need to carefully think about how we present the material. What we want to do is reduce redundant material and information that causes students to split their attention. So what we want to do is reduce information that is not critical for learning the material, and we want to make it easy for students to find the most important information on a slide or when we present the material in some way. We also want to reduce the students' need to work on problems that they have not created the required schemas for. So if they don't have the domain-specific knowledge structures in their brain to solve a problem that we're given to them, what they will use is what's called means-ends analysis. That is, they're going to try to figure out how to solve the problem, but the process adds so much cognitive load to their working memory that they will experience cognitive overload. And therefore, even though they probably will solve the problem, they will not learn how to solve the problem for the future. That's kind of like what happened when my son drives to the store. It also turns out that we can actually increase the processing power of the working memory by doing what's called dual processing, using both vision and auditory channels for processing information. We can actually increase the limited capacity of working memory. So when you think about the PowerPoint I just showed a little while ago, maybe you just show the diagram on the PowerPoint and then you verbally describe what's going on in the diagram. That way they can use the two processes to increase their working memory and therefore learn more material that you are presenting to them. Okay, so we have tried to control the intrinsic load of the material we're presenting and when we are presenting it. And we're also trying to choose a style of presentation that will reduce all the extraneous material that just takes cognitive load without actually adding anything to learning. Okay, so now what? What should we do? Well, how should we design our courses in order to maximize learning, given the intrinsic load and extraneous load have both been controlled and reduced? Well, what I'm suggesting is that we have to use what cognitive psychologists have offered us in terms of evidence-based teaching strategies. So in general, I'm just going to talk about 4 of those right now. There are 4 ways that we can use to design our courses that actually increases the germane load of the material that we are presenting, the activities that we give the students to do. The first one is to take advantage of what's called distributed practice or spacing. So what we need to do is space out the presentation of our material. So students need to see the material more than once. So instead of cramming all that stuff into one lecture or one study event, what you need to do is spread it out. So maybe you introduce the material week 1, you review it in week 2, you give some formative assessment maybe at the end of week 2, you review week 3, and then they study for the material before the midterm in week 4. So that you want to spread it out over time as much as you can. And the longer you spread it out, the more memory will last. The second thing is use what's called interleaving practice. Interleaving is, when we present material in class, we often give one concept in one class, and then we have students practice it. And then in the next class, we give another concept, and we have students practice it. But then when it comes to the exam or real life, material is not presented like that. Students have to solve problems that come at them from all kinds, so they don't know exactly what type of problem that they will be facing, and therefore they don't know what solution method to use for each problem. So what they need to do is train to not only solve a problem, but also to choose and select, to discriminate between different types of problems. And that's what interleaving is all about. So what you do is mix all the problems together as much as you can, and then have students work these problems, because then they have to first decide, okay, what kind of problem is this? What kind of solution method should I use? And then secondly, they will apply it and see if they can actually solve the problem. That's interleaving. The third one is retrieval practice. All right, so it's one thing to get all that information into the long-term memory because it's going to be there. It's unlimited. It's going to be there forever. But for effective learning to occur, students have to be able to retrieve that knowledge on demand. And that's not automatic. You have to practice that. And that's what retrieval practice is all about. So, we know about the testing effect. One of the best ways of learning something is to test students, ask them to retrieve things from the memory, and every time they do, that path gets stronger and stronger. They make more and more connections, and learning just becomes more durable. So retrieval practice is actually one of the most important things that you have to practice. Give lots of formative assessments, not only summative, give a formative assessment without a grade, just for them to practice retrieving information. Finally, Elaboration and self-explaining is also very important. In order to make learning very durable and strong, the students need to make connection between the information that you're teaching them right now and previous information they have learned about, as well as the life experiences they've had in the past. So asking them to do such things as structured reflections or elaborative interrogation, that is asking themselves questions of why is this happening, what's going on, why am I using this method? All those kinds of questions and reflecting on the information makes the learning a lot more strong and durable and more useful in the future. All right, so those are 3 things you can use for increasing the germane load. That's very effective if there is some space left over in the working memory, which is why we have to reduce the extraneous load and control the intrinsic load first. But if you can do all of those things, then what you will be able to do is maximize the learning. You can solve that constraint optimization problem and promote learning among your students. Thank you very much.